Right, so I think it's being recorded. Yeah, so okay, so 6:26 is to end. So that means there's a lot of P2P until 6:21. So 6:21 today is, well, there's a lot of week, right? Another 3 weeks, 4 weeks. Okay, so that means we may continue our lecture for the next 2 weeks to come. But we're going to have since we are going to have a lot of time until the June of 26, 21, okay, whatever. So maybe the 3rd week in June, right? So maybe we can take longer time to complete our lecture. So maybe next week we do not need to have our test since we still have time. So we could just have our test in the last week, right? Probably in the 26th, or no, maybe in the last 3rd week in July, in June, not July, in June. So I'll let you know. But tentatively, let's try not to make the test next week. Not, or if you want to, we can have the test on next week, next Friday. If you don't like it, maybe we have it until the last week of this semester, which is the last week in the 3rd week in June. Okay, the 3rd week in June. Okay, so let me know your preference. Okay, tentatively, I would like to have it on the 3rd week in June. So that is the very last week in the semester. Okay. So anyone want to tell me anything? It's a long holiday. Forgot what to do. I'm doing something else. Forgot what to teach. Okay. But anyway, we still have some materials to cover, which is just a revisions of what we have done so far, which is on simulation. Okay. So last lecture, we have spent a bit of time to tell you what to do if you want to simulate your animations, right? So the idea is very simple. Just use this code, then you'll be able to show the simulations. But the important thing is like you have to have a set of parametric equations. So in this case, this is the parametric equations, right? So you have to have equations that changes with time. So you displace the profile of a functions for every t, right? So the profile will be displayed on the same screen for t equals to 0, t equals to 1, t equals to 2, t equals to 3, whatever, and then display it on the screen. Then when you do it like this, then visually it will mimic the video. Okay, so last week, and you are supposed to do the assignment as well, to do a simulation for the wave, right? So today we are going to continue with the example of simulations on displaying a 2D projectile. So this is another classical example, right? So when you teach people how to do the simulation in physics, this 2D projectile motion is a very classical idea. So let us spend a bit of time to talk about this one. It should be very simple to you, right? So before, again, as I mentioned in last lecture, when you do a simulations in physics, right, the first thing you want to do is understand the problem. You have to understand the physics of the equations given. Now, if you have a good idea of what the equation means and the significance of it, then it would help a lot for you to perform the simulation. So again, the simulation is sort of a technical procedure. So simulation procedure is divided into roughly two parts. Right? The first part is to understand the concept and understands the background, understands the physics of this equation. The second part of it is to translate the knowledge into a code. So I would always say the second part of the translation into the code is the easiest one. Right? So I usually spend some time to explain about the physics. So when you look at this equation, you have to understand what is the interpretations of these equations. So we always start with the interpretations of the equations you want to simulate. Right? So y represents the coordinate of an object that is being shown in a projectile. So you have a projectile. then you have to understand that in the projectile you have a set of equations derived from the Newton's law. So if you write down the Newton's law of equation and solve it, then you find that the y, which is the height of a projectile, is dependent on time given by this formula, and then the x coordinate of it is also given by this formula. So these x and y are the so-called solutions in the analytical form for Newton's second law in the two-dimensional projectile motion. So you don't need to solve any differential equation, you just obtain the analytical solution. So this is the analytical solution for the second order differential equation. And so the x and y are the coordinates. So if you look at the equations very carefully, the x and y here can also be understood to be a pair of parametric equation. Okay, so this is not different from a set of parametric equations. If you know how to simulate any set of parametric equations, then you can do these questions very easily. Many simulations that we're going to see in physics are expressed in terms of parametric equations. So this is parametric equation in terms of x and y, where the parameter is t. Another example, I think the other example would be with this one. This is what we're going to do next. When you do a simulation for an interacting box, then the parametric equation here is this. The x is a parametric equations. The x is the parametric equations and depend on the time t. Right? So in this case, you have x and y, also a set of parametric equations. Okay? The x and y again represents the coordinate of a box, of a ball in a box. So in another example here, this is also parametric equations, but this parametric equation is slightly more complicated. So it describes a point of A when A has two coordinate xa and xb. Then there's another point called B. It has also two parametric equations. So in this example, rotating equal triangle, in this example of a box of particles in a box, and also in this example of a 2D projectile motion. So they are all parametric equations, okay? All these parametric equations depend on parameters, so you change the parameter t from 1 to 2 to 3. Okay, so let's come back to this 2D projectile motions. Any projectile motions has its own physics. So you have to understand that when you throw a ball into the air, you have to specify two initial conditions. You have to specify the velocity of its the initial speed. So in this case, there is a V0 that is used to describe its initial speed. So V0 is the initial speed. And then you have also a parameter that describes the angle where you launch the projectile motion. So these are two initial conditions, the projectile angle theta, as well as the initial velocity V0. And this is a two-dimensional physics problem, right? So you have to resolve the motion along the x directions as well as along the y directions. So you write down the solutions for the equations of motion along the y directions, and then you will solve it, and this is the solution you get. Y equals to y at 0 plus V0 Vy0 t minus half dt squared, where this Vy0 t is the initial velocity along the y directions. So this y0 is nothing but just V0 cos theta, no, V0 sin theta. So Vy0 is the initial velocity, right, when you launch a projectile. So Vy0 is not expressed here, but it's understood to be V0 sin theta. Then V0x is initial velocity of a projectile along the x directions, and it is just given by V0 cos theta. So this V0 cos theta is nothing but just the V0x. So I'm making a revision with you. These are the 2D projectile motion that all of you should have learned in your 101, in your also physics. Okay. So given this set of equations, then you are going to simulate it. So I've explained to you the initial condition in terms of V0 and theta. Now what is next you need to know? Next thing you need to know is about the scale of the problem. Now the scale of the problem, as I explained many times, the scale of the problems, you have to understand there are two scales in this case. When you do a simulation, you have to just estimate how long you want to simulate. That is, how long, how many time steps, for how long, like 1 second, 2 seconds, and time step. The length of the time is what you have to decide in the beginning. You also have to decide the size of the simulation box. Right? So how large you want to simulate, like when you throw it, that projectile motion, it will expect to reach what height, to reach what width, right? So in this physics problem, the natural scale for the time involved is just t half, right? T half is the t half is the time that is used for the projectile to reach its maximum height. Whereas r is the size of the spatial distance that refers the range, right? So you throw a ball from one point, then it will, I think, okay, I'm going to show you the answer. So this is the height, right? This is the height h, and then the range is from this point to this point, right? So this is the height and this is the range. So before you do the simulation, you should understood that, yeah, the size of the box I'm looking at is roughly of this size, r, and you can derive the height and the r from theory, right? So you just, how do you estimate r? R is the height from here to here, right? So from here to here, so the time taken from this point to the half of the maximum, to the maximum is the t half, right? So you can calculate the time to the t half from this point to this point. So using v equals to u plus at, and you set at the maximum height v equals to 0, then your t height, the time taken to arrive at t height is just given by this. So this is half time to flight. Half time of flight is very simple, right? This v half, the v half, the t half is easy to calculate, right? It's from this formula, right? You just set v at 0, and then you calculate that. So v equals to u plus 8 gives you this. So once you know the time of flight, half of the time of flight, then you can calculate this r very easily. The r is just the velocity along the x component, that is v naught x, times 2 times the time of flight. So the time to go from here to here is t half. From here to here is another t half. So the time to flight from this point to this point is 2 t half. So you multiply the values of 2 t half by 2 multiplied by v naught cos theta. That will give you the distance travels by the projectile within 2t. Then the height again is just v naught along the y directions multiplied with the t half. So basically, you know what is your y as a function of time. So you slot in t equals to t half into the expression of y. Then when you simplify this, you get the h. Right? So h is obtained simply by substituting t half into the y, which means that the time taken from here to here is t half. Therefore, this is the height. Y at t half is just the h. So you obtain the height of this much, and then this. So you use this r and h, then it will help you to decide how large you want to fix the box, right? So when you do a simulation, you have to decide what is the maximum width of the box. You want to fix that, and then you want to fix the height of the box of simulation. So this r and h will give you the idea of how large you want to fix the box, right? And then t half is the idea that lets you know how long you want to simulate it, right? So you simulate it for maybe 2t half. 2t half is the time taken from here to here. So what I do is that I estimate 1 half, 1t half, 2t half, 3t half. 3t half will simulate the beginning until the maximum, go back to the range, and then fall down for another t and a half. You can of course let the t to go to another t half, then it will just go down further. But we're going to simulate for some idea for 3 times the t half. So the t half, r, and h is listed here with the purpose to let you decide the scale of the time and the length scale of the simulation plot. Okay, so once you know that, then you can start to do the simulations very easily. So you write down a formula of a function that would generate the values of y and x at different t. Then you let the t to run from 0 to 3 times t half. Then you set the box size to be of r and h. Then you call up these things. I think this is what we do. You call up this display clear, display, put it into a for loop for t, then you do the simulation. Okay, so so let us try to simulate this. So I hope that I can do this within maybe like 10 minutes or so. If I take too long, then maybe I'll just let you to read this. So basically, I'm going to reproduce this number. Okay, I'm going to reproduce this number here. So first of all, you need a numpy, you need a matplotlib, and you need IPython package to do the display. Okay, so this is what you do. Then I'll just run my enter. Okay, so that of course there's no problem. So the first thing I want to do is to initialize my code. So to initialize my code, what I need, okay, sorry, to initialize my code, wait, let me close this. Okay, so to initialize my code, where is it? Okay, to initialize my code, I have to, to initialize my code, I need to know what numbers I need to initialize. Initialize means that you provide the constant that will be required for the simulation. So what are the constants? Look at it. So you need the constant. The first constant will be g, right? So 9.81 is the constant value you put in. And what else are the constants? So you need to provide the initial constants. There are two initial conditions. That is a V0, which is the maximum, which is the speed of your of initial launch, and then at what angle, right? So I'm going to fix V0, right? V0 to be, say, some number. Normally we choose 1 meter. 1 means 1 meter per second. So this is the default. Then you choose theta to be 45 degree, right? 45 degree. 45 degree means 45 times 45 degree. You want to have, but the theta has to be expressed in terms of radian. So you have to convert this into radian. So 1 radian. So 45 degree times np dot pi divided by 180. So this is a factor that will convert 45 degree into the corresponding radian, right? So 45 degree, how many radian is that? So just print it out. Theta. So the theta value 0.78 is the values of the angle 45 degree in unit of theta. Okay, so I'm just repeating in case there are people who do not know how to convert from angle to pi to radian unit. Okay, so next thing we want to do is to define the initial values of the angle, the initial values of the x component. Right, so initial values of x component is just nothing but just V0 multiplied with cos theta. Okay, with cos theta. So this would be the initial values of the projectile motion along the x directions, and then V0 y is defined to be the not this cos np. This is np. Dot multiply with np dot sine theta. Okay, so this would be my V0 x and V0 y. So this is the V0 x and V0 y I'm talking about. V0 x and V0 y. Okay, so then I will have to define the time scales. Like I will call this T half, HALF. So I define my T half to be the formula. So the T half is just nothing but V0 multiply with sine theta and p sine theta divided by g. Okay, so that would be my T half, and then I would have to fix my R. R is defined as x0. Now x0 is initial coordinates where you launch a projectile. Usually you fix your x0 and t0 at the origin. So x0 is 0, y0 is also 0. So this is the initial coordinates of x and y naught. So my r is just x naught plus 2 times t half times v naught times cos theta. So I have been typing a lot, so I will have to run it to see whether I am making any error. So I'm already press the shift enter and don't see any error. That means so far there's no typo. So once I have defined the r, then I define my h. My h would be y naught plus v naught. Okay, so it's plus v naught sine theta t half. So this would be v naught times sine theta, v naught times, okay, t half times sine theta times v naught. So this should be my sine theta. But for the y component, since it has a gravitational pull, so you have this extra term, right? So it's obvious that this half gt squared is the gravitational force. Now this term half gt squared is not found in the x component because x component do not suffer any gravitational pull. Okay, so that's how you interpret the physics. So you see and you understand that this term minus 0.5 times gt squared times g times t half squared. Okay, so that is what I expect. So assuming that I have not made any stupid mistakes, so I have initialized my constant. So now I'm going to define my functions of x. The function of x is to be defined in terms of the parameter t. So again, x is very easily understood to be x naught plus, so this x is the values of the initial constant, which is x0 plus v naught t. So the x is to be returned to be the values of x0 plus v naught x. Okay, v naught x multiplied with t. I think that is the constants, well, not constant, the equation of motions for x naught plus v naught xt. So that finished the definition for x, and then we're going to define the definition of y. So y is y naught plus v naught x, v naught yt minus something. So this is y naught plus v naught t. So this term is the same with the x, but what happened in in y is that you have this additional half gt squared, which is not found in the x component. So you have this additional term minus half gt squared that will contribute to the parabolic shape on the trajectory of the two-dimensional problem. So g times t half square. Okay, so that is the y and x. So now we have x and y. Okay, then you have to decide what is the time to run. So this is defined as TLR, stand for time variable expressed in an array. So it will be arrange, and then you want it to arrange. You want it to be from 0 up to t half. THALF. Okay, so how many t half you want? So let's say we want to do it for 3 t half. So this 3 t half is what we call as t. Usually t is a quantity symbol refer for the period. Well, here I will not take it as period, but we take it as the total length of simulation time. So we want to simulate for 3 t half. And then let's make it as say 50 point. This is default, whatever. But you don't make it too large, you bring it to it small. I think 50 is a reasonable time. So once you have done that, then we are ready to plot the graph. Okay, so this is before you do a simulation. You always plot the graph. You plot the graph for X and for Y. No, so you want to plot XARR. XARR is an array that is generated in the forms of an array, which would show you all the expression of the value xt for t in TARR. Okay, so this is the array for X, and then you can also have an array for Y like that. So now we are ready to plot XARR and YARR. Like anything? No, of course, because there's a stupid error here. plt.plot. Okay. No, why I get nothing? So what happened? So for t in TRR, y in YTR. So what happened is blank. So some stupid mistake must have been done somewhere. So what is my XARR? XARR should be a number. No, it is not, right? So the XARR should be an array, but it doesn't look like there is an array. What's the problem? X array, Y array, define, blah, blah, blah. But why is it X is always 0? And how about Y? Y array is also 0. No, also it's not right, because Y for T in ARR. Okay, so anyone can tell me where is my problem? Anyone can tell me where is my problem? Why is that I always get only 0 for my X? X naught, so it's defined X naught defined as 0, X naught XT. Okay, so let me try this. X at say T half. Let's get some number. Okay, so I don't have a T half. T half. Where is my T half? Is it any spelling mistake? No. So T half should be a number, right? So T half should be a number. So when I print out, yes, there's a number X at T half. Okay, so I think what is the problem then? XARR T half for T in ARR. So let's define this again. It should give me an array, but I only get a for T in TARR. Okay, so no one want to help me on that. Why is that my Y does not return an array value for me? Yes, let me check my answer. Okay, I think theta is not defined. No, I think theta is defined though. Theta is defined. Theta should be defined. Theta is defined. So X is defined. So I think I forgot to define the theta, but it doesn't matter at this moment. I should be able to show that the values of YARR and XARR should appear. Define. Okay, so let me stare at the screen. Anyone want to help me? No one want to help me? What's the problem with my code? TARR, do I have any number? TARR. Okay, so I think that the problem is with TARR. TARR should be an array. NP, no, this should not be like this. I think it should be lin space. Okay, so it's lin space from 0 to 15. So now it looks better at least, but it's not working as what I expect. It doesn't look like it is a parabolic curve. It should show a parabolic curve instead of showing me only a straight line. So maybe some problem is shown here. So why not this one? Why not V naught? Okay, so let me show it for a longer period of time. So maybe say 10. Okay, no, this is not the correct curve, right? So even though you plot it, you know this is not right, because what you expect is a parabolic curve. Why should change with respect to x squared? So what I'm showing here is that when you do a simulation, you should be able to tell whether your output is correct or not. Now this is very sure the output is not correct, because it does not meet the expectation that the formula, when you solve it, the x and y should be such that y is proportional to x squared. So now there's a lot of troubleshooting that we need to do here. So to make sure that things is doing correctly, t half is done v naught y. So make sure that v naught x, v naught y is not 0. So maybe it's a v naught x that is not defined, v naught y is not defined. So okay, v naught x, v naught y is defined correctly. V naught x, v naught y multiplied with t half g t half squared. So y, okay, let us try to look at the print instead of this. Let us print, for example, x and then t. So y versus t ARR. Now this, what do you expect? You expect that when you plot y versus t, this is what you will see. So you should see y should inversely proportional to t squared. So I'm in the process of doing a troubleshooting, okay? So this is not right because it does not look like a parabolic curve. So the y that I got here doesn't give me the right value, right? So the y that I got is not right. Right? So y naught plus v naught y times t minus half gt squared. So gt half, t half squared. Okay, what's the problem with this? Anyone can tell me what's my problem? Why is it my y is not giving me the correct behaviors? So the y does not go in the right directions. T half, no, it's not true. Right? So I'm still doing a troubleshooting. Y TRR is not right. It doesn't look like this. So if you run this correctly, you should see that the output should be like this. Let me plot this. Theta plot x. Okay, y should not be t half on half. Okay, so people show me this. Let me see. Y half, y equals to v naught minus half gt squared. So what's the problem? Let me see again. Any suggestions? So when you think that yt should be t, not t half. Okay, so y should be t but not t half. Yeah, okay, so this is right. So this should be t. So if I put it at t half, it becomes a constant. So there's no wonder that the y only depend on t, but do not depend on t half. The reason is because I made a stupid mistake that this should be t but not t half. So this is half gt squared. So this should be gt. I should be looking at this, okay? But I look at this t half square instead. So t half is a constant, but t is a variable. So now, thanks very much for Benny, I think, for helping me in this. So I got the right y dependent on t. Okay, fine. Okay, so yeah, it's Benny. So you see it's lengthy because the time I displays is 10 t half, and if it's 10 t half, then the change actually is most drastic around this area, but you don't see the peak to rise, right? The reason is because in this part that I show here is just not been highlighted because I have extended the time to be 10 half. Okay, so I should string this back to 3. Then you should see clearly that yes, there is a peak around here. Okay, so this is to show t versus r. So I'm going to show y versus r. So yes, this is what I expect, right, for y versus x. Okay, so now you have this y versus x. Maybe we should plot x-axis and y-axis. PLT plot axis h line 0, and then the PLT x v line 0. Then what happened? A x v line. Okay, this is a line. So you see a line here, then there's the reference point, right? So this is where x naught, y naught is. This is a peak. Okay, so now we have just displayed this. We have done this in the first exercise, I think in the very beginning of this course. So now we are ready to do the simulation. So let's just do the simulation bit by bit. So I need this. I say I need to this, and then I need all this display thing. Yeah. So we do it one by one. So now once you have done that, so we are going to do it later. Okay. So okay. So let me close this. I think we don't need to plot this at the moment. I close this and I close this for a moment. So I'm going to write a for loop for t so that I can display the simulations. Now I need x. Now this is already defined. Okay. Okay. So not. I think it's defined. So I'm going to define my x array, y array here. Then this is just to prepare a frame where I'm going to show my subplots. Then this is to clear if there's any display on that subplots, clear it. After you have cleared it, then prepare the display again. Then I'm going to show my PLT show. Okay, plot PLT plot x array, y array. So that is a statement that asks it to plot. But I'm going to plot not using this method. I'm going to plot using this AX. Okay, so this line says that I'm preparing a subplot, and then this subplot has a label. Its frame is labeled as AX. So I'm going to use this AX to do my plot. So instead of doing this, I say AX.plot, so that this plot is plot on the axis of AX or on the frame of AX. Now the good thing about this is that you can customize the AX. Okay, so once you have done that, then you say you can AX. You can say I think set say X title, set title. I think title equals to say Y versus X. So that would set the title for the axis. Then after that, then you said okay, you're going to show plot show PLT dot show. Okay, I think it's like that. I forgot. Sometimes I forgot. I'm not very good at remembering things. Okay, so if I press button, do you think I get the simulation to show? Now this simulation, even though we show, it's not going to work very well because I have not set the axis frame, fix the frame yet. So that's of course an error as usual. So I think the axis set title is wrongly spelled. So it should TITLE. So now there's no error. But it does not display anything. What happened is that okay, no, this is not showing anything. Okay, so let me clear it and then save it and then clear all my kernel, restart and see if there's any miracle happen. So let us run it. Is it running? Yeah, it is running. And then there is an output. Let's just run it again. Do I see any simulation? No simulations. The reason is no simulation because I just asked the plot to plot the default, right? So you should plot it as a point, right? So maybe that should show me a moving ball when t changes with time. If I get it, then we can proceed to the next exercise. So it's not done yet. I have to stop to restart this. Okay, now we have this, but it's not showing any simulation. So it looks like my simulation is not working. It should work, right? Because t is changing with time. Okay, I think the reason is because of this. I think it's because I'm using this to plot TAR. So this should not be there. Now see, I plot it, and what is shown is the TAR is XARR, YARR versus XARR. But it's not supposed to be this because I'm plotting it wrongly. So I'm not supposed to plot this. This is meant to display the projectile motion without time dependence. Okay, so this is just reserve it when you want to plot the projectile in a full line, only then we use it. But here we are not supposed to do that. We are supposed to plot the x versus t and y versus t. Okay, so I make mistakes, then you learn from this. So that is the correct way to do. So you plot x t y t for every t. If you plot xar yr, that is what you get. You will not see any changing coordinates, right? You should see only that case. So this is a changing coordinate. Okay, so it is doing well, but you see this changing because we have not fixed the axis. So we have to fix the axis. So the axis is fixed based on this ax. So we are going to do this ax. What was the formula code for fix that? So the fix is plot limit. Okay, so you have to plot the limit from where to where. Okay, so we are going to fix the x coordinate from where? From 0, which is from x0, x0, up to what is the maximum. So the limit should referring to the range, right? So it should be 1r or 2r. So that should be the correct way to fix it. So I think we should fix that r. But r is too short because you are actually flying more than the range of r because the time is 3 times t12. So this should be roughly 1.5. Okay. Okay. So half t. T12 means that the time of flight is to reach the maximum. So 3 times of 3 T12 means that the x would travel through a distance of 1.5 times the range of t. Then you also show the y limit. So y limit is starting from y naught. No, not actually y naught. It should start from 0. Okay, because y naught, whatever it is, so it should be the limit should be from the lowest to the highest. Okay, so the lowest is 0, not quite. You should start from the lowest to the highest. So the lowest is 1, and then this is the highest. The highest should be h. Okay, the lowest, is it 0? No, it's not. The lowest is this, right? The lowest plot is this point, right? So what is this point? This point is a value of lowest y. So what is the lowest values of y? You look at this formula. Lowest of y happened when y occurred at t of y at t. Right? T, I'm referring to the last period. Right? So your last time, your last values of this should be of y evaluated at t. Right? So this should be the lowest value in your y limit, and this is the highest value of the y limit. And then the left hand limit for your axis should be 0 and 1. So this setting of the x limit from left to right, y limit from low to high reflects how well you understand the physical system, right? So if you know what is the range, then you should be able to evaluate it, and then you put in the correct number. So if you put in simply something like 1, 2, 3 or now 22.5 via trial and error, you will still do the simulation, it will still show, but when you change the values of the initial conditions, then your plot would not be perfect. Sometimes it will be too small, sometimes it will be too large if you change the initial conditions. Okay, but if you were to express your size of the simulation box in this manner, then it will become scale invariant, meaning that when you change the initial condition from V0 to say you don't know what values, your time simulation to become say 5 times t12 or maybe 0.5 t time t12, or you change your theta to be, let's say, to 133 degrees, then your box will still show quite nicely. Okay, so you see this. Okay, so now to fix, you have fixed the box. So this is fixed and starts to reach the maximum, right? Then it will then come back and then it will touch at the lowest point where y values is calculated to be y at the capital T. So it will reach this very end here, right? So it's very precise. The box size is very precise. You don't see it because it is the ball is finite size, but it's only 1/4 of it is shown here. So you also want to then display this part here. display this stuff onto this. Okay, so what you do here is that you define your XARR and TARR like this, then you paste it here so that when it plots, it will plot this together with this. Okay, so this AX plot and the plot for the trajectory will be merged together. Then you see this. Okay. And on top of that, you also want to include also the axis with AX vertical line 0 and also then horizontal line at 0. Where is it? Should do it again, run it again. Okay, so now you include this horizontal line and vertical line, so it's all included. Now, if you want to do it for different trajectory motions, say at angle as 45 degree, you change it to say some other number, say 30 degree, okay, maybe 15 degree. Okay, then what do you see? Okay, wait for a while. It's taking time to reset. Run again, yeah. Now you don't see much difference, but except this angle, but it's not obvious to the eye because the scale has been set in such a way that you see a nicely proportionalized pictures. What I'm saying is that if you change from 45 degree to 30 degree, visually to your eye, these two pictures or these two submissions look like similar. Now, it is not the same. The reason is you look at it as the same is because of the scale, right? So because the Python automatically do the scaling for you. So what should we do is, again, I had mentioned last week, so you have to fix the scale. Right? You just fix the scale to 1, 1. I think that's a fixing of the scale. Where is it? You set the scale to become fixed. That is a scale. Where is it? Let me see. I think last week we have I think here, you have to have a scale. You set the aspect ratio to become equal. Right? So we would like to set the scale so that the X and Y are in the same scale, so that when you display for different theta, the graph should appear differently. Okay? So other than fixing V versus X, then we also fix it. So for the frame AX, we set the scale to be having aspect ratio equal. So now you see this, right? So this aspect ratio is launching at the angle of 30 degree. So if you change it to 45 degree, whatever, here the angle is 15. Okay, so let me show it here. Theta is 45. Now it's 15 degree. 15 degree means that it is quite close to the horizontal. Okay, so it is 15 degree is very close to the horizontal. So the height it reach is like this large. But if you change it to say larger, saying 45 degree, 45 degree, maybe make it larger, maybe let's say 75 degree. Then when you see, you will see visually the projectile should looks differently. Okay, so now you see this, right? So now fixing the scale to become aspect ratio equals will impact how the simulation appears in the box. So when you do the simulation, adjusting the aspect ratios is a very important factor, right? So if you don't adjust the scale to be equal, then sometimes what you see will be sort of like this geometrically distorted. So those that are equal in size will look different, or those that is equal in size would look the same in the X and Y directions. Okay, so I'm displaying to you, this is how you do the simulations. And if you want to add in extra thing, then you just add in. For example, you want to add in the X-axis label and Y-axis label, then you do it here. So instead of title, you say, I think X label equals to X, and then Y label equals to Y. I think that will also show you Y in meter, and then This is y label and x meter y. I think it should work. Okay, so now you see y is labeled and x. So now you'll be able to label everything. The bad thing is that sometimes it's flickering. I do not know how to fix this. There are better ways to do the simulation, but you try and figure out yourself. This is only the only way I know how to do a simulation. I think there is much better way to do simulation in Python. So I'm just telling you the simplest one because this is what I know. Okay, so we have finished simulating the two-dimensional box. So now let's just go to the next example. So this is a more complete version, right? So I have also printed out the values of the x and y coordinate and things like that. So the one I show on your screen, like this one, and the one I give you, the code as example, is slightly different, but the idea is the same. So my code that I shown here do not have the theta in the argument, right? So I just add in t, but if you want to add in theta, then you can do that as well. The code still works. So there are many ways, more than one way to do the code, but you just have to be flexible in your thinking when you do the coding. Okay, so when you run this, that is what you get. Let's see this again. Okay, so now we see that the ball is now going from time to time, and then this is a very nice simulation. Okay, so let's just go to do the other example, which is more interesting. This is called a bouncing box. About a bouncing points in a square box. We call it a point here instead of calling it a bouncing box, because the summation that we do here is assumed to have no size. So you only see a dot. The dot that looks like it has finite size, but it actually has no size. If it has a size, then the ball should bounce against each other when they meet. So we are doing a simulation where we assume the points has no dimension and the particles could go through one another without interacting with each other, but they only interact with the wall. Like a point will interact with walls in the sense that when it bounces the wall, then it just reflects on the wall, or it just go through the wall from this side and then enter another side. So this is a very simple simulation. We did it all the time. Last time when we did this in Mathematica, we asked the students to do a simulations in 3 dimensions. Okay, so if you're interested, you can try to do the simulation. Instead of a box of 2 dimensions containing points or particles, you can do this for a 3-dimensional box with many particles bouncing inside the box randomly. And then in order to make things more interesting, you could make the particles to be able to bounce against each other with a finite size. So say let's say the ball is a ball, not a point, then the ball have a finite size. When you have finite size, when they go through each other, if their cross section does not overlap, then they just pass through each other. If the ball has finite size, and if they pass through, if they now move through each other, and the cross section meets, then they will bounce off each other, and the bouncing should be following the conservation of linear momentum. Okay, so that is another simulation. Last time we used to have time, then we do it, right? So this could be one of the very interesting exercises for you to do. If you have time, maybe we can go through that. 3-dimensional finite size ball that bounce off each other following the conservation of momentum in 3 dimensions. So this is the most complicated versions of this kind of simulation, but not the most complicated. Not the most complicated. The simplest version of this is a box of 2 dimensions with finite size, containing 1 ball or 1 point, and the point will just bounce within this box. This is the simplest versions. Then the second simplest version would be you have more than 1 point. You have, let's say, 2 point, 3 point, or NP points of points inside a box. Then this point will just bouncing off each other, bouncing off against a wall randomly. So this is what it looks like if you do the simulations. Right, so we have like 20 balls. They move, and then when they move and meet the wall, then they will just bounce off, going in the opposite directions. So conservation of momentum is obeyed because the directions is just reverse when the point bounce off the boundary. Total energy is also conserved So this is the simplest, well, second simplest version. Now the more complicated one that I mentioned just now is will be like three-dimensional box with finite ball size, and then they would bounce off each other. Then when they bounce off each other, you have to conserve momentum. So this is called a hard ball model, right? Though the ball is finite size and they're hard in the sense that they don't interact with each other unless they touch each other. So this is a contact interactions. So this is the second interest. This is the second most complicated situations. So when you do that simulation, you are actually simulating a what I call a Maxwell-Boltzmann system. The Maxwell-Boltzmann system are systems where the particles are ideal particles. When you study these statistical mechanics, for those who have studied statistical mechanics in your second year or third year, you have a box of particles, then they would bounce off each other. When they bounce off each other, they have to conserve the momentum. When they conserve the momentum, energy or kinetic energy will transfer from one ball to another. So that is quite complicated, but the interactions of transferring energy from one ball to another is only happening when they touch each other in a collision course, right? So if they don't ever touch each other, like what is seen in your simulation, then there's no way for the systems of particles to exchange energy. So this is sort of like idealized but hypothetical system. You don't really have that system in reality because all systems have a finite size. The particles, like those containing air molecule, they will constantly interact with each other. But the interaction in the molecule in the air is much more complicated. They are not only having, they don't really have these contact interactions. They will actually interact with each other and change the energy or the kinetic energy of each other through what I call action at a distance interactions. Okay, so that is what we call in the domain of the molecular dynamics. Okay, so molecular dynamics means that you have particles or molecules that is contained in some box, and then they would move freely before they make collision, but they are getting close to each other, then they will interact with each other through a action at a distance interactions. So that is really a complicated system. This is a realistic system, but most idealistic system are those systems where you have Maxwell-Boltzmann distribution, right? So those systems that you learn in your statistical mechanics, ideal gas system, they would constantly exchange each other energy through collisions. Right, so this is a hard ball model. So through those collisions, that energy will be distributed. So finally, you would have an equilibrium system where the distribution of the temperature or the distribution of the velocity will follow what I call a Maxwell-Boltzmann distribution. So for those who have gone through your statistical mechanics, you may understand what I say. For those who never, then you may not know what I say. But what I'm saying is that this simulation can be brought to a very complicated level to simulate a realistic three-dimensional molecular dynamic systems. You can actually use that to predict the behaviors of gaseous system, okay, or solid system, or whatever system. So we used to do that. But we are not going to do that. Okay, last time the first time when we introduced this course, we do teach molecular dynamics. We ask people to write codes to simulate that kind of molecular dynamic system, which is kind of interesting, but for most of you it would be too complicated. Okay, but I'm just mentioning this to let you know that the simulation can be made in a simplest manner, but in reality you can also make it to become complicated to really describe or predict a realistic system. Okay, so that is the preliminary of these particles in a box things. We'll take a break. 5 minutes 4:02 now. We come back at 4:10, 4:10, 4:08, 4:10. Okay, 4:10. 4 o'clock 10 minutes. We meet again here. Okay, then we'll continue our discussions. So we'll take a break for a moment. Any questions? You can post it here. I'll try to answer your questions. So this is the attendance. For those who have not taken attendance, please take your attendance. Okay. Okay, so we resume our lecture. Okay, so continue with this. Okay, so now you see my share view. There's about 21 people. Well, where is the rest going to? So I said it's 4:10. Okay, so we wait until 4:11, then we begin. Okay, so let's begin on this simulation box. So now to do a simulation box, you have to consider now step by steps the conditions for a box. Right, so this is a box, right? So first of all, to do a simulation of a box, you make sure that you have to set the size of the box, and then you have to choose how many particles you have with the box. Okay, so that is the first thing you do. So size of the box and the number of particles of the box. So here I choose 20. Then after you have decided the size and numbers of particles, then you have to decide where the particles should begin at. So the particles should be initiated to locate at some positions inside the box in the beginning. So you should see at the beginning there is this particle sitting there at time t equals to 0. So where are they supposed to be located? So you have to initialize the initial position. So where are these positions? This position must be initialized. Now using some method, there are many methods to initialize the conditions of the initial position. One simple way is to just randomly initialize, right? Just randomly generate a number, two numbers to represent the coordinate of this particle, then displace the point at that randomly initialized coordinates. So this is a random initial condition. Now the other way is to just, for example, draw a grid, right? So you draw a grid of say maybe like 20 times 20, then you place on each of these grid point the particles, right? So these particles are arranged nicely in some kind of a regular grid. So this is usually done in the molecular dynamics simulations. Okay, so you define your crystal lattice, then you know where is your lattice point, then on each of these lattice point, then you locate the particles in this lattice point. Then you have a crystals, right? So this is the first initial conditions. That is the initial condition for the position. Now, what is the next? You also have to make the particle to have initial velocity. Like according to Newton's first law, if there's no force, well, if the particles is constantly at rest, initially at rest, it will constantly at rest. If the particle is moving initially, it will continues to move, right? So this is the first law. So if you fix the particle in the beginning without any initial velocity, the particle should fix there and stay forever. So this fact could be checked by looking at this very simple formula. That is the velocity of the particle if it's 0. So if the velocity is 0, then the particles at the next steps and is the same as the particle at the initial the step before it. So you cannot have the v, that is initial velocity of the particle, to be 0 in the beginning. You have to initialize some value. So again, you have to choose random conditions such that the particles initially, each of them should have initial values of velocity. Now, since this is a two-dimensional problem, you have to initialize the velocity along the x component and as well as along the y component. Okay, so you have, for each particles, you will have four in total initial condition: the x coordinate, the vx velocity, y coordinate, and the y velocity. Right. So these are the initial conditions you have to set in the beginning. After that, then you let the particles to evolve as a function of time. That is, the particle will change from this position to the next position. Now, what is the change of the position? So Newton's law says that now the change of the position is just given by this very simple formula. Like v x in the next position is just the times delta t times the velocity between this. Right? So at time t n and time t n minus 1. So this is the previous step. This is the next steps, and the two steps are separated by a gap of time called delta t. Right, so this is the delta t. So the delta t gap will change the position from x at tn minus 1 to x at tn. So the difference between these two positions is the displacement. So the displacement is just simply given by the velocity of the particle multiplied with the time intervals between them. Right? So you have to decide what is the smallest time interval. Right? So after you have initialized the coordinates, initial position, and the velocity of the initial conditions, this is Vx naught and Vx and Us. So the V here is constantly not changing, right? So they are constants. It's not like in the gravitational field where the V will change. So this is a idealistic systems. Velocity that you initialize will remain the same magnitude throughout the whole simulation. So the Vxi, Viy here refers to the initial velocity along the y and initial velocity along x component for particle I. Then they will evolve quantity. So at different time t, the positions of the particles will change. X coordinate will change, y coordinate will change. Right? So if you discretize the simulations, if you discretize the equations, then you arrive at this equation. This equation and this equation are equivalent. It's just that this is the one that should goes into the simulation box. So you discretize the equations, then you look at it, and then you just write down the equation, the positions of the I particle at time tn and the particle at time tn minus 1. Right? So then they are just simply given by the constants times the intervals between these two positions. So you have to choose the delta t to be very small, right? So that every time the positions will be displayed to change a little bit by a little bit if you choose your time delta t to be small enough. Okay, so you run through this loop for all xi, and then run the n. Now the n here refers to the time parameter. Right? So when n equals to 0, it corresponds to t0. When n equals to 1, it corresponds to t0 plus 1 delta t. N equals to 2, it corresponds to t0 plus 2 times delta t. Okay, so you have to simulate this one by writing a loop for I, and then put the for I loop in the for n loop. So you have to have two loops in order to do these simulations. Okay, so you have to decide these few parameters, these few initial conditions I mentioned just now, the size of the box, and this one, number of particles, then to initialize the coordinates and initialize the initial velocity, and then you have to choose your time of simulation, right? So what is the time of simulation? Again, you have to think, what is the size of the box and what is the length scale of the box? Okay, the length of the box is, of course, is L. So this is simple. The length scale of the system is just L, is just fixed. But what is the time scale? The time scale is roughly the time taken for particles to move from one end to another. Right? So you start off the particles from here on the left hand side, it goes to the other side. So what is the time scale? Then the time scale is given by tau. In this case, the tau is defined to be just simply equals to tau is just simply equals to the size of the box divided by the initial velocity or the typical velocity of any particle. So you assume that inside the box, the initial velocity should not vary so much. So it should not vary from, let's say, 1 meter per second to 1 million meter per second. No, it shouldn't be like that. It should be roughly like for the particles in, say, air, roughly the velocity is roughly, I think, 300 meters per second, or something like that. Maybe not 300 meters, maybe slightly faster than that. But roughly it's 300 meters per second. So the velocity, typical velocity should be more or less the same for all particles. Then on average, tau is an estimate of the time scale for this particle. So you have to decide what is the initial velocity. So this is what you have to initialize, right? So you choose the initial velocity to be, say, between, say, 10 to 20, right? So just simply choose one number between 10 to 20. Then the tau is just given by this. So the tau is a very small scale. It's a scale that tells you roughly within one tau, particle would have moved from one end to another. So if you want to do a simulation, then you ask yourself, if I do a simulation, how long should I run? So let's say I run it for 2 tau or 3 tau. It means that roughly within that simulation box, within that simulation time, you will see a simulation roughly. You have a particle moving from one end to move to another end for one time, then come back to another time, then come back again to so about roughly move to and fro for 3 times. So that would be roughly the length of the simulations that you would see, right? So you set the length scale to L over V naught, then you decide the total time of simulation T to be just some multiple number of n tau multiplied with tau. So this n tau could be 1 at least. 1 means that at least the particle will move from one end to another. So, but this is normally, that is not enough, right? So you want to do a simulation, you want to see simulation at least for the particle to bounce back and forth at least for one time. So it goes from one end to another, it's 1 tau. So it comes back again to another side is a 2 tau. So roughly you have to at least simulate for 2 tau, right? So maybe you can make this n tau to be say 4. It should be a reasonable estimate. So you would not want to make the tau to be too large or to be too small, okay, for simulation purpose. But in molecular dynamics simulation, usually the total simulation time is much longer, like millions of steps, whatever. Now we have to define one quantity called delta t, right? So this delta t is defined to be time step, right? So it's a time step which is very small, right? So so these time steps is defining the time between the particles at one point and at another point. Okay, so there are a few quantities that you could think of. First is the time scale tau, then total simulation time t. Right? So this t usually is a macroscopic number, maybe like say 5 seconds, 2 seconds, 1 second, or maybe like 60 seconds. Okay, then there's another number, which is the number of steps. So one step is delta t. So you have to decide how many steps or snapshots of simulation you want to do. Right? So you take one snapshot, you move from t to 1t, and the second snapshot is from 1 delta t to 2 delta t. Another snapshot is from 3 delta t, 2 delta t to 3 delta t. So the time will evolve from 1 delta t, 2 delta t, 3 delta t, 4 delta t, up to the millions or maybe hundreds of delta t. Right? So this delta t is one snapshot, distance of one snapshot. So you have to decide nt. Now, nt could be saying maybe like 200 or 300 or 400. So if you do see this simulation, right? So every flickering, when the particle moves from one snapshot to another snapshot, that is a difference of delta t. Right? So if you set the delta mt to be say 1000, that means you are going to see 1000 snapshots that keep on changing. Right? So within these 1000 snapshots, the particle will roughly move through a total time of t, which means that roughly the particles, one of these particles would roughly move through some distance to and fro along the box for n tau time. Okay, so as a summary, you have to choose delta t by defining t to be say 4 times the tau, and then you have to decide the nt. So nt should be as large as possible, maybe 100, 500, 400. And then once you have chosen the nt, then delta t will be fixed, right? Because t, capital T, is fixed by the values of n tau. Once the total time is fixed, then the distance or time steps delta t would be fixed if you set nt to be say 100, 1000, whatever. Okay, so once you have fixed this, then you will start to write down the parametric equations. Then you would generate the coordinates of these particles at every t. Once you have generated the particles coordinate for every t, then you should be able to simulate the positions of these particles in each box, one frame after another frame after another frame for a number of frames which is specified by the nt. Okay. Now, what happens if the particles keep on moving? Then it would bounce onto the wall, right? So when it bounces on the wall, you have to decide what happened. So there are what you call a boundary condition that has to be fixed Boundary condition means that what happened to the particles when they meet the walls. So there are two conditions. One condition is to just bounce back, but these particles have to conserve momentum. Okay, so this is called a fixed boundary condition. Particles that bounce on the wall should reverse in the directions exactly the same as previously without change in the magnitude of the velocity. So this is a fixed boundary condition. The other boundary condition is called a fixed boundary it's a periodic boundary condition, meaning that particles that goes into this box, it will come out from another box. Okay, so that is called periodic boundary condition. So the fixed boundary condition is very easy. It says that if the locations of the particles is outside the box, or so there are two possibilities for a particle to be outside the box, right? So either it's on the left-hand side of the box or right-hand side of the box. So left-hand side, say x start from 0 to L. So when x is larger than L, that means it's going into the outside of the right-hand side of the box. When x become negative, that means the particle is going to the left of the box. If you fix the particles box to be between 0 and L, right? So every steps you check the locations of the x coordinate. Once you identify the x coordinate, as long as it come up once larger than L, then you have to revert the velocity. Or if the particle's locations or the x coordinate is become negative, that means it goes up to the left. For the first time, you must revert the velocity immediately. Along the y direction, the same. So you monitor the y for every steps of t, and all the while the y should be between 0 and L. Once y starts and for the first time to be larger than L, then you have to revert the positions. Or when the values of y become negative, you revert it. So this is called the fixed boundary condition, right? So periodic boundary condition looks like this. So when x is larger than L, then it would be replaced into these coordinates. So what is this? If the x is larger, sorry, let me say it again. If the x here become larger than L, that means it's going to the right hand side. So in this periodic boundary condition, the particle has to be placed on the left hand side again, and so it's coming in from the left hand side. So you think about it, the locations where the particle should re-emit into the box from the left hand side has a coordinate of x minus L. Okay, if the particles is going out from the box towards the left hand side, then it should enter from the right hand side, and the coordinates of the right hand side should be L minus L plus x. So when in this case your x is a negative value, so L would minus with some small number. So this L plus x is actually referring to the coordinate, which is, now look at the mouse, which is on the right hand side, which is close to the right end. Okay, so this is the mathematical expression that describes a periodic boundary condition. This is a mathematical equation that should describe the boundary conditions, which is called fixed boundary condition. So these are all the things that you need to know. Then you just sit down and start to code it, right? Now the important aspect of this has been explained. If you really understand the situation, to translate this into a code is a matter of just a matter of doing it, right? So you should not find it very difficult as long as you understand it, right? But it will be difficult if you don't understand at all what you are doing. Okay, so let's just do this. So let me cut and paste the initial thing. So that is what I'm going to do. I think we should have some time to do these simulations. You have exercises and also have assignment to do as well. So again, you have these random conditions, and then I have to set the parameters. So I have to set the size of the box to be at 1 meter. Okay, then I choose to do a simulation for 1 particles, or well, 20 particles. It would be good if I do it for 2 particles, just to show you how it looks like. 1 particles can also be done, but maybe we just do for 2. But later on, when I change NV to 20, you should be also to see the same thing. So they have to choose the initial conditions for the speed. But the speed has to be chosen to be some number. Okay, so there are, let's say, 2 particles. So I'm going to define the initial values for the initial speed as a factor multiplied with V0. So V0 is a constant, right? So I'm going to generate, say, for example, a fraction number, random number. That random number multiplied with V0 should then be assigned as initial value for the particles, right? So this is just a constant that I'm going to choose. So roughly all the particles in the box should have a constant value, or should have a magnitude, roughly, okay, not exactly, not every particle which have the same velocity or have the same speed, but it will roughly be at this scale. So then I define my tau, which is the length scale, the time scale of the particles. So it should be the length divided by the typical speed of the particles. Okay. So within one tau, particle will bounce from one end to another. Okay. So then I decide how many time of the bounce should happen for the whole simulation roughly. So I said 20. That means I expect the particles to be bouncing from left to right for 20 times. Before the simulation stops. Okay, so that is roughly what I expect. So I just set a number. Then T, which is the total length of the simulations, should be 20 times the length scale. Okay, so this is the absolute values of time. So this T should be running for 20 times the time scale of the problem. Then I decide that I want to show 750 snapshots. Each snapshot is different, well, is delay, well, is the time for one snapshot and the time for next snapshots is defined by delta t, where delta t is a small number on time, which is the total length of the simulation time divided by 750. So I'm going to simulate 750 snapshots. Each snapshot will display the instantaneous positions of all the particles. Okay, so if you increase this NT to become, say, from 750 to say 1000, that means you have more snapshots, and then the simulation will be finer. The particle will move more smoother. Right? So if it's very close, then you see that the particles change in velocity is like, no, it's not that smooth. Like when one step to another, particles change in position could be quite drastic. But if you make the simulation such that the delta t is smaller by increasing NT, then you see the simulations will show a evolutions of particle system which is smooth. The particle will just move like they are following a gradual change in the position instead of like, you know, disappearing from one point and appear at another point which is quite far away from the initial frame. Okay. So, but anyway, this is just the initial number that I choose. Once you have chosen that, then what do? You have to then show a box. Right? So the simulation of a box, display the box and display the particle in the box. Okay, so you have to fix the coordinate system, right? So you have to fix the coordinate system. So how do you fix the coordinate systems? I think this is what you want to do. Okay, so you have to fix. I think you do a fixed spot and then you do this. I think this is what I want to do. Okay, so I'm going to do it step by step. So before I simulate it, I just want to simulate a static frame. And then in this static frame, I'm going to show a plot of the particles. And then I want to see and set the limits of the box. Okay, so the box would be set to a size of 0 and L, and 0 and L along X and Y directions. And then this is the matplotlib command to set up a plot which is labeled by AX. Then I'm going to plot the coordinate of the particles X and Y. Okay, so this is the coordinates for the particles X and the coordinate for the particle Y. So how do I assign the particles X and Y? So let me do this. Okay, so let me do this one by one. Okay. So first of all, I have to generate my initial velocity. Okay, so I have to use random. Okay, so what I do is I use random. So let me try to print random. See if I can print a random. Again, number. No, I think the random is not called properly. Let me see how do I call my random number. the random number is called using random. So in this case, I have to import random package so that I can use a random. Okay, so I think random. Let me see if I can do this without that. np random, no. np random, no. Okay, no, it's not like that. Okay, anyway, maybe I just use random. So I'm importing random package and I'm going to call this random. So the package random has a function called random. In this, it will give me a number random. This will give me a number which is lying between 0 and 1. So this random number will be multiplied with the V0. So this would generate the random number for my particles, one of my particles. But I have how many particles? I have 2 particles. So I have to write a loop for I in NB. Then V0 for V0 X for the particles number 1, the values is equals to random times V0. Right, so this random times V0 will generate a random number, and the number will be assigned as the initial velocity for the particles number 1. And this is the values for the initial values along the x direction. But this is not going to work because here I'm using V0x as an array. And this array has dimensions of NB. But I cannot do that because I have not defined what my Vx0 is. Now Vx0 is a random number, is an array. So I have to declare my random to be an array that has NB entry. So this should be array. No, it should be np.0. So I think this is fine. I think by doing that, you are declaring the Vx to be an empty array which has dimension of nb. So without using this, when you run this, you will not work. So I'm showing you this. So I run this, I have error. Because here V0x is not declared, but as long as I declare V0x to be an empty array with NB element, then it will work. But somehow it doesn't work as well. There is some stupid mistakes I've done. For I in NB, no, this is of course not true. So I in range of NB, okay. And then also has a problem, the range, okay, not a problem. Okay, so now it's done. Right, so I have successfully assigned V01, V02, which refers to the initial velocity for the x component of particle 1 and particle 2. But I have to do one more for the y coordinates and x coordinate, for the x and y velocity for the x component and y component. But that is not enough. I mentioned that you also have to initialize the initial conditions for the x coordinate initially. So initial conditions or initial position for the x coordinate is defined to be a number. Right? So I assume the number should be between 0 and 1 multiplied with L. Right? So this will give me a number which is lying between 0 times a random number multiplied with L, and this random number should not be larger than 1. So these values of x should always be lying between 0 and L. Right? So that is the coordinate of the initial particle. All the particles should be lying inside the box. So that is how you do it. So you also then define an y coordinate, and they should be all lying within the box size of 0 to L. So this is to denote the fact that the x is all lying inside the box of L. Okay, and this x should always be within L, and y is also should be always within L. I think this is what I'm saying here. Okay. So again, this would not work very well because I have not defined my x and y as a random as a array. So I'm going to do this for the y component, and then also do this for the x. So x in this case is an array, and y is an array. So this is something which is sometimes a bit not as convenient. If you use Mathematica, then you don't have to declare this empty array. It will just assume by itself. So that is what the Mathematica is better than Python in this sense. So I press a button and let me clear my memory just to make sure that I do not keep all the past history, and my code should always be starting from clean. So I press the button and I have run it. There's no error. Okay, so I have already initialized my x coordinate, y coordinate. So now is the time for me to do the plot. Okay, so I'm going to do the plot to show the plot with a fixed limit of x and y. Then I'm going to plot what? Plot ARR and YRR. Now, what is ARR and what is IRR? So of course, then the XRR should then be what should be? It should be the collections of all the coordinates of x and y. Am I right? Not quite true. Let me think about it. So if you want to displace the coordinate of x and y, so this is what you do, right? So this is the coordinate of x, particle y coordinate for particle y, right? So this would be the x coordinate of particle y and y particle y. So let's say you have this x1 and this x1. So let me plot the particle y. Let me plot the particle x1 and y1. So this will show me the coordinate of particle x1 and y1. So I'm going to show this and plot it once. I don't get anything because x1, not x1, that it should be in the bracket. Okay, and then y1. Okay, so this is going to show me the location of particle 1 only. Again, it's a syntax error, so this should be plot ax plot, and there's an error invalid syntax, so this should be not x1 y1. Yeah, okay. So I'm showing this particle x1 y1. Okay, so let me print out the coordinates for p1. Print out x1 and y1. Okay, so let me try it again. So this is the coordinate of 0.23 and 0.22 times L. Okay, I should times this with L. L is 1 anyway. Okay, so this is 0.75, 0.13, so 0.75 is here. So this is the coordinate for particle number 1. Now, how about if you want to print out the particle number 2? So the particle number 2, well, how we want to show this x2, y2, right? So this should be x2, y2. That would be quite difficult to do it, right? So let's see, when to print out the x2, y2, you would have to do it like this: x2, y2. I'm showing you the long way, right? So the long way is like this. So I have particle number 2, y1, print out particle number y2. Okay, so y1, y2. So there is an error. What's the problem? Is our bonds in the size of 2. Index 2, x2. Okay, sorry. Of course, it's not y2. It's 1 and 0. Okay, so I've always got confused. So this should be 0 and 1. Okay, so there are two particles. The particle number 0 and the particle number 1. I should start counting from 0 instead of counting from number 1. Okay, so I should start this from for particle 0. Particle 0, particle 1, particle 1. Okay, so that should show me 2 points. The first point is this, 0.83 and 0.69. So one is 0.83, 0.69. The other one is 0.86 and 0.63. So you have these two particles. This blue one is the first one, and then this is the second one. So let me try it again. So now it looks like you have two particles. One is 0.7 and the other is 0.95. So this is 0.95, this is 0.7. So try again. I want to see a discretely different point. Okay, so this should be close to 0. So it should be 0.95 and then close to 0. Okay, so this is all correct. Now, let's say if you have 20 particles. Now, how do you define the plot? If you have 20 particles like this, then it would be how to do it. That would be a bit complicated, isn't it? If it's more than 20 particles, so you have to think how to put this together. So I'm going to think this like this. I'm going to think this as ARR to be collections of okay, let's see. I think this should be XI, YI, like this for I in a range of NB. So would that works? I am not sure. That would not generate X ARR, Y ARR. Okay. So I'm not really sure if this is working. Okay. So there is a valid invalid syntax. So that should be like this. Okay, so again there is an error. Okay, so now I'm showing you in order to proceed with the simulations, then you have to think what is the correct way to displace the x and y coordinate for all the particles in the box. So basically it should be like this, so maybe I just do it like this. Throw it like this. Let's see what happens if that's the case. I see no point. I'm still doing this. Still doing the arrange. Okay, so it doesn't show up correctly because the syntax is not right. So now I am asking you how you would do this, right? How to show the x coordinate and y coordinate of the particles in the box. So I think the correct way to do it like this is that when you want to plot it, you have to plot it FARR for all the x coordinate and y coordinate. Okay, so it looks like the correct way to do this is like this. Is that you have to collect all the x coordinate, right? And then you put it into XARR, and you put all the coordinate of y into YARR, and then you just plot the XARR, YARR, and then with things like this dot. Would that work? Yeah, it looks like it's working. So that's how it works. But let's just check if this is true. Okay. Now, if I'm doing this correctly, I would expect that the coordinates that is displayed on the screens should look the same. Okay. So I'm looking at this one. So what is the coordinate of this? This should be like close to 0 and 0.2. So I print out close to 0 and 0.2. So this refers to the coordinate of this. This is the coordinate of roughly 0.8 and 0.7. So 0.8 and roughly 0.7. So I'm checking the coordinates that I generated from the random x and random y for particle number 1 and particle number 0. So I print out their coordinates, and then I look at the screen and I verify that indeed the coordinates, two particles are appearing at the correct coordinate systems that I expect. Now, this is very simple, right? It's trivial. You generate the number. You make sure that you want to check. You want to be sure that the coordinates are correctly being represented by the printout on your screen. Now, if this line of the plot is not correct, then you will find out that the particles that is appearing on the screen would not having the correct coordinate. So what I'm showing here is that it's just again a process of checking. You always do the checking of the code. Now you generate 4 numbers, random number, and you see 2 points, and you expect 2 points. Okay, so you say I'm done. This particles has been clearly displayed on the screen, and I'm happy. But if you make some stupid mistakes, then the coordinate that are generated may not be correctly captured by XARR and YARR as printed on this slide. So I just want to make sure that when I use this syntax, indeed the coordinate is being displayed in the correct manner. It's just a process of checking your code. You don't always accept whatever appears in the screen as correct. There's a way for you to do a correction or checking. You always do a check. So I spend a lot of time doing checking, right? The code is fast, you can drive it very fast, but checking sometimes takes a lot of time. So I'm trying to train you to have this attitude of always be careful and check the output of your screen, of the output whenever you do a code. Okay, when you write your code. Okay, so now it looks like we have been able to generate a code, and let's try to make the numbers of particles to become, say, 10, and then see if you got it right. Okay, so I have these particles, 10 particles, all are setting at the random coordinates, right? If it's not random enough, just make them more random. Okay, so roughly it is appearing in this one. But again, the x and y axis are not set at the same aspect ratio. So let us set the aspect ratios again to make the particles, the simulation, to make the simulations to looks more to make the box more square. Okay, so you make the box square. Okay, so now the box is square. So it represents a square box with 10 particles moving in a set in randomly sprinkled inside the box. So that is the initial conditions for the positions. So then we can proceed to then define the positions of the coordinates at different time according to this formula. Okay, so let us write it here. So then we can begin doing this. So you initialize the code, and then you let me throw this away. Now you have seen the initial conditions. So we begin the definitions for the x here. Okay, so we define your x coordinate again. Would that be a problem if I define my x to be like this? I think should be okay. Okay, so that is what I'm going to do. I'm going to define my x coordinate here, and I'm going to define my y coordinate here. Okay, so I'm going to write another loop to go through all the I index where the values of I, the value of x at I would be evolving, right, according to this condition. Right, so every values of the x should be replaced. Sorry, not this one. I'm sorry. I should be looking at this one. Every values of the next instance of time for x should be replaced by this coordinate. Okay. So now to translate this line of code means that the values of the previous x, well, the values of the previous x should be replaced by the previous value plus Vx times delta t. Then this whole expression would then be replacing the current values of x. So this is just a increment in time. When time increase from tn to tn plus 1, then the values of x would be replaced by the previous value plus this. Okay, so I'm explaining to you, and to translate this into the value here should be like this. The values for x should be replaced by the value of x plus Vx of I multiplied with delta t. Okay, so this is an example to say that the values of xi will be replaced by the original values of xi plus this plus its velocity times delta t. So delta t has been defined somewhere here. So this is the delta t. So it's number that is small, which has been defined. Okay, so this is going to run for time for t in some t range. TARR. Okay, so I have not defined my TARR yet, which I'm going to define it here. So the defined TARR should be like this. TARR is the linear space. It's a linear space for the time. So it is an NP linear space for time from 0 to the total length of time, and then let's say I just define for how many time steps for NT. Right? So 10T is the numbers of snapshots. So it's going to run for this length of time, and you have to then have 750 snapshots. So this is my TARR. So the first T values in TARR is 0. The second values is 1 delta T. The third value is 2 delta T, and so on and so forth. Okay. So I'm going to let T to run in TARR, and for each T, I'm going to run my for loop for the X. So be careful, there will be two loops. One loop is to run for the time component. The other loop is to look through all the particles, or all the points, and there are 20 points in this case. Okay, so you have to have two loops. So every loop is happening at a fixed t. Okay, so that is how it looks like. Xi, Yi. Okay, we still have a few more minutes to go. Sorry to keep you. Okay, so that would be like this. So that would be giving me the values of x and t. Okay. So when I press button, and there's an error. Now, usually because Vx naught is not defined. So Vx is V not x. Well, the initial conditions and the Vx is the same as Vx. Okay. So if I refer to this one, I am assigning Vx naught, but the Vx naught and this Vx I and Vyi are the same because they are constant. Okay. So once you have done that, then maybe I should do this, right? Maybe I should do this. I should say, once I have initialized the conditions, then Vx is then just equals to the constant. Now it becomes constant for Vx, and then the velocity for the y component of particle I is then again another constant. So I'm going to use Vx and Vy to define the constant velocity, which is the formula or the term that appears here. This is Vxi and Viy. So I'm going to call Vxi, and Viy using this term. So Vxi, Vii. So this is my Vxi, Viy. So like Vx is not defined. Vx is not defined. It's already defined, isn't it? This is Vx. Okay, yeah. Now Vx is a velocity, and then this Vx, and when I use it like this, it is an array, right? So, but I have not defined my array, so I have to define my array here as well. So, but this is more or less the same, right? So this is an array. The Vx naught is just used once, but most of the time we're going to use Vx and Vy. See, the difference between Vx naught and Vy is just a matter of pedagogy. I just want to make a distinction between the initial value and the values of Vx or Vy at subsequent time. It so happens that in this model, the velocity does not change in time. But in more general situation, the initial velocity and the later velocity for a particle in a box in general may not be the same, but in this case it's the same. That's why we assign this line here. Okay, so now it's done. Okay, now we have been able to do this. So let's just try to simulate this. Okay, so we're going to simulate this. Okay, we are going to simulate xi and yi. Maybe like this. XARR, okay, yeah. So let us cut and paste this one, and then put it in the X loop. So once the for loop is exited, so let me do it like this. Now the locations of the tab is very important, okay? So this is the for loop for I, right? So once you exceed the for loop of I, all the values of xi and yi has been calculated. So then here I define my xarr, which is calculated after the for. So when I do this xarr, it means the for loop in the above has been exceeded. So maybe I just keep a tab here to signify that this line that appears here calculated after the for loop in I has been exceeded. So I'll be able to collect all the xarr, yarr coordinate, and then I'm going to plot them and then see whether it works for all these t. But since we're going to here, since we are here already, maybe we just simulate all the videos by doing this display. Okay, so this display, by doing this display. Okay, so for all the display, it will be like this. Okay, so I'm going to do the display and see whether it works. No, yes, no. Indent for I, there is an incorrect indent. Okay, here it should be this. It should be this. See if it works. No, yes, no, yes, no, yes, no. Okay, so it takes some time. It is waiting. 5:02. So I'm taking a little bit of your time. So I'm eagerly waiting to see whether the simulation will appear. If it doesn't appear, then we would have to delay the lecture. No, I have to stop this and then I have to interrupt this and then try again. Okay, I'm going to start it. I think it's going to work. I think. Hopefully it works. No, yep. Kernel restarting. Okay. So it's still restarting. Yep. Okay. If it works, then we can finish. If it doesn't work, then we have to continue next week. It's just a few more minutes. Kernel restarting. Kernel restarting. What happened? No. Stop it and restart again. Restart. Okay, run again. Is it working? Oh, okay, still waiting. Okay, it's restarting. Okay. No. Nothing come out yet. Sometimes we need a bit of patience. But this is basically the structure, okay? If there's no syntax error, then it should work, okay? So I have evolved all the x and t based on this coordinate, this very simple code. So the most important line of code is this, okay? X and y is evolving according to this coordinate system, according to this line, okay? Now we have not imposed a boundary condition yet, but we are here. Okay. Now, if you wait for another minute, it doesn't come out, then we have to terminate, and then we will begin coming back to these questions next week. No. Wait. Okay. No. Why it takes so long? Is it because, no, I think it's fine. 750 is fine. Is it too long? Okay, now I'm not going to wait. I'm going to restart all again, but I'm going to reduce this to say 100 just to make sure that things come out. And then instead of 10, let's just make it say only 3. Okay, I'll save it and then I run it again. Okay, it looks like it is. No, is it? No. This is not. It's not. Yeah, okay, this is the one I'm looking at. I'm still waiting for it to come out. unsaved changes, save it, checkpoint created, and the simulation, where is it? Oh, run, press the run again, no, run, okay, so I'm checking, looks like the GPU is using a lot of memory. What is using memory? So Firefox is using memory, so it looks like it is running, but for some reason it doesn't show up. Stop and run again. Start and run. Nope. Okay, time's up. If it doesn't come out, then we just have to stop here. It looks like something is happening. It's just that it is not showing up for some stupid reasons, which I don't understand. Kernel, yes, kernel, run, yes, cell again, run again, run. Okay, kernel, whatever. Let's wait. I think sometimes it would take some time to display the simulations. Maybe my memory is full. The RAM is full. That's why it doesn't come out. Yes. Run again. No, there's no effect. So we just have to stop here. Hopefully that when we come back next week, I'll be able to show you the simulation. So since we cannot finish this part, so I'm not sure whether you should do the assignment, because the assignment asks you to do the animations for the simulation box, but maybe you can't. So again, it takes more than 2 hours for me to explain the part 10 for you. So we can't do the simulations for this moment. We just have to wait for a while. Okay, so we just have to do it. This looks like it is plotting. Is this the one that is doing here? Yeah, I think it is. It looks like it is showing, but it is not showing correctly. Okay, so there will be no assignment this week. I'm going to delay the assignment. Now my purpose is this, since I cannot finish explaining this, so I'm going to delay the assignment 11. So today there will be no assignment, okay? At least I give you some time to do some other assignment. But today assignment will be delayed until this Friday, okay? So that's all. I'm sorry to take up some of the time. So it's 5:08 now. Any questions you want to ask? Either you ask it here or you ask it in the WhatsApp chat group. Okay. So that's all for today. I'm going to end it here. Okay.